Hello everyone, my name is Maria, and today I'm going to talk about adversarial generation of informative trajectories for dynamic system identification. What is dynamic system identification and why do we do that? So, classic robot control relies on accurate models for robot dynamics, which basically means knowledge of actual physical parameters of the robot, such as weights of the links and maximal velocities of the joints and maximal angles of the joints. Most methods rely on generating a single long, exciting or informative trajectory. Hang on a second. What's exciting means? Exciting in this context is the same as an informative trajectory. That's the one that helps to bring out inertial parameters of the system, such as maximal angles and velocities of the joints and weights of the links. So as I said before, most of the classical methods rely on producing a single very long trajectory like that, and it's usually computed using evolutionary or gradient-based approaches. Now the issues with that, that exploration is limited within the set length of such trajectory. Moreover, optimization can get intractable for certain lengths of such trajectories. Instead, we propose to use multiple cyclic trajectories using modified Fourier transform. Such trajectories can later on then be stuck together and represent this one long exciting trajectory. Then further, we propose to generate these trajectories with GANs, models that are known for their diverse and realistic generation. So what's the benefit of our approach? Well, mostly the speed. So shorter trajectories can be optimized in parallel, which makes the whole process much faster. And then replacing the part of optimization with generation of the new exciting trajectories with GANs makes it all even faster. So first a little bit of theory. This is rigid body dynamic equation. Tau is the full joint torques as experienced and measured by the system. M, C, G, and F are correspondingly inertia matrix, Coriolis and centrifugal matrix, gravity vector and friction vector. And Q, Q dot, and Q double dot are position, velocity, and acceleration. So now, if we rearrange the rigid body dynamic equation with the regressor y, tau is still the full joint torques as experienced and measured by the system, and pi now are the inertial parameters, the system parameters that we are looking for. We could just use least square approach to solve it, and it would work for a single state. However, unfortunately, not only we have multiple states, but also multiple trajectories. So what we do instead, we stack the regressors together as a huge matrix, and we stack the torques for each state together, as you see on the slide here. And then we rearrange again for pi for the inertial parameters we're looking for, and use the pseudo-inverse of the regressor to solve this equation. So now the problem is if y transpose is ill-conditioned, so has eigenvalues close to 0, the numerical errors can occur in our expression for pi, and that would mean the regressors would be ill-conditioned, and hence the produced trajectories would not be exciting, would not flesh out the relevant inertial parameters pi. So the goal of trajectory optimization is producing trajectories that are well conditioned for y transpose, and that's exactly what we call exciting or informative trajectories, which means basically just accurate estimation of pi, the inertial parameters we're looking for the system. So for comparison, if we try to optimize the trajectory, a classic exciting trajectory that's 10 minutes long, we would take about 8 hours, as compared to if we convert it into short cyclic trajectories using modified Fourier transform. They would take 6 minutes each trajectory, which is 3.5 hours, so that's more than twice faster, to be combined into a 10 minutes long exciting trajectory. GAN training on some of the exciting trajectories, that would take about 40 minutes. However, then it's just a second to generate 10 minutes worth of exciting trajectories. So it's definitely a huge win in speed. Now, a little bit of theory on GANs. So classic GANs architecture involves two networks, generator and discriminator. Generator inputs noise and produces some realistically looking data, in our case trajectories or trajectory parameters. Discriminator then looks at this data along with the real data and tries to decide which of them are real and which are simulated. The SIDE-GAN, the main modification made to classical architecture of GANs, is attempting to assess the realism of these trajectories, not only in terms of the trajectory parameters themselves, but also eigenvalues of these trajectories. So if you look at this scheme, the gray parts of the scheme are pre-trained and the weights are fixed for the training time of the rest of the GAN. So first of them, predictor, predicts the validity or faultiness of the trajectory. What do we mean by that? Sometimes trajectories generated by GAN can be not valid in terms of the self-collisions and bridging maximal torques and stuff like that. So this predictor literally is just trained on good trajectories and invalid trajectories generated by the previous vanilla GAN, and literally just predicts whether it's valid or faulty so that the system can be later on penalized on that. The converter, the eigenvalue converter C, is basically a pre-trained neural net, a very small one, that converts the trajectories into pseudo eigenvalues. Now, the eigenvalues can be calculated directly, however, it takes way more time than just predicting them with neural nets, and the accuracy is also pretty high. And the discriminator, the second discriminator, looks at the eigenvalues of the system and tries to identify whether they look like real eigenvalues or fake eigenvalues, because we have examples of both. So, as if you look at the training objective function, you can notice that it's pretty much classic vanilla GAN objective function. However, the last line accommodates for this branch with predictor and converter and additional penalties of whether the trajectories are valid or faulty, and also whether the pseudo eigenvalues look like diverse enough, good enough trajectories. So now, what about these diverse enough and good enough trajectories? What about the fitness? There is a few ways of trying to figure out whether the trajectory is going to be exciting enough without directly rolling it out and checking whether the system parameters can be calculated efficiently. So there is two fitness measures that can be used for these purposes, and we actually do both of them, and they perform relatively close to each other. So one of them is condition number of y transpose y. So that's the ratio between the largest and the smallest eigenvalues of it. So if you imagine the parameters spread out in multidimensional space as a ball, that's roughly how round it is. The other one is diagonal fitness, and that's the diagonal of y transpose y, except for here it's the maximum divided by minimum. So now again, if you imagine the parameters, inertial parameters spread out in a space as a ball. That's how big it is, intuitively. So we roll out our experiments on a KUKA ARM4. We have 1800s of trajectory parameters. So they are represented by 7 by 6 by 2 tensors, where 7 is the number of joints of KUKA, 6 is the number of modified Fourier transform parameters, and 2 is 2 points in space that define a cyclic Fourier trajectory. Each of these cyclic trajectories is 16 seconds long, and we also have corresponding eigenvalues for all of them for training this second branch of SIDE-GAN. So here are some illustration of SIDE-GAN generated trajectories. As you see, all of them are quite diverse, so they don't look like each other, and in this specific case there is no self-collisions, nothing gets broken or no joints explode. The ratio of valid trajectories generated by SIDE-GAN is actually quite high, it's above 70%. That said, DCGAN produces only about 4% of valid trajectories. That's to explain why do we need this whole second branch to our SIDE-GAN. Here is a visual example of what it looks like when we roll out our experiments. So single long classic trajectory is at the top right, training data, so modified Fourier cyclic trajectories that we use for training, stacked together, 35 of them in fact, are at the bottom left, and there is 35 of GAN-generated trajectories stacked together at the bottom right. As you see, both training data and GAN-produced trajectories are quite diverse and at least appear exciting. Here's an example of a summary of classic trajectory, multiple cyclic Fourier trajectories, training data set, and SIDE-GANs. So as you see the results, in simulation, single long classical trajectory definitely loses to multiple cyclic trajectories, and then SIDE-GANs perform even a little bit better. Same happens in real world, with the exception that multiple trajectories produced with modified Fourier transform versus SIDE-GANs. Although features some positive results, it's quite a small difference, quite close to inconclusive. Other than that, we also provide an evidence that SIDE-GAN performs better than vanilla DCGAN. And the result you see at the top is adding the SIDE-GAN generated trajectories or vanilla GAN generated trajectories to the original training data set, and the improvement in the precision in normalized mean square error torque predictions that it creates. So the first column is the most important one. It's just literally adding the generated trajectories to the training set and checking on the performance on normalized mean square error of torque predictions. The second and the third columns are literally there to show that just adding more of training data with various noise doesn't really make a positive improvement necessarily. And the table at the bottom finally is the parameter estimation quality. It shows the confidence of inertial parameters prediction. As you see, both SIDE-GANs with eigenvalues and diagonal fitness scores represent the best and close to the best results. And that is it. Thanks for watching, and please do let me know if you have any questions.